where you have a lot of local minima, right? That's the problem here. Local minima, not so good for gradient descent. You can see this lattice thing at work. It evenly spreaded more or less the design points. It's not like you have a cluster here and nothing here, for example. That's the thing. Other than that, you can see that there's no correlation between those. And there should not be one, because those are not really constrained in any way. Hi guys, today I want to talk about the Design Explorer. This is a relatively new feature in the Inspire world and covers a direct approach to do design of experiments. So what is it? In simple terms, it lets you optimize a design where you not really know what are the relationships between two different variables. So for example, if you just have a parameter optimization and you don't know anything, or if it's highly nonlinear, or you don't know anything about the system, typically that's where hyperstudy comes into place. And I would say, so the Design Explorer is a simple form of hyperstudy in Inspire. So if you have Inspire, you can use this, and I would urge you to do this because it's a really powerful tool, especially in nonlinear situations. Why is that? What's the difference between this and the more typical structural optimization approach, like with the topology optimization we will cover in this video? And for that, I wanted to go and take a step back and just compare those two methods, the design of experiments and the gradient-based optimization approach, in a small code example, because I think it's pretty easy to show it there. If you know all this and the theory is not a thing where you want to dive deeper into, just skip ahead. I will mark it in the time and you can skip to the tutorial with Inspire directly. All right, that being said, I would say let's jump into the code. So basically I made up a little bit of a problem. So I will also share this code with you, so you can go into GitHub and just dive into this and run it on your own. And if you want to know more about how to set such things up, please let me know. For sure, I would like to go deeper into this one, but I will keep it brief here. So, all right, what's the problem here? So optimization, comparison, gradient-based, and DOE. Just imagine you have this function, like x minus 3 to the square plus y plus 1 to the square. So this thing here has a global minimum at 3 minus 1. So x being 3 and minus 1 being y, and 0 is the output of this function, right? So if you put in 3 here and 1 here, you see, and minus 1 here, you see that this is leveling out, and then you have just zeros. Okay, yeah, just to get a little bit more of a visual understanding of that, I have this here. So I just can make a little plotting. So this is the function basically. If you go to GeoGebra or so and just plot this function, this is what you will get. And yeah, Matplotlib is not the best tool to do it, but it was a quick shot right now, so bear with me on this one. All right, so this is the function, right? Going back to the problem setting. Now we have this function, and our search is the global minimum, because optimization can be, yeah, I would say it can be brought down to this simple term. You have something you want to maximize or minimize. And in this case, it's a function where we have two design variables, x and y, and we want to find the minimum value for the z variable or the function variable. And this is similar to, for example, a structural optimization, for example, topology optimization. You want a design where the design variables are the densities of each element. So is it a part of the material, or is it just empty? Does it contribute to the stiffness of the part? And the function, what you want to achieve is, for example, minimize the compliance. That means maximize the stiffness of the part. All right, so you can think of optimization in that context, like you have a bunch of design variables, in this case element densities, and you want to adapt the densities like so that you have your function minimized, in this case compliance, or maximized stiffness, right? Okay, so this is a very simple thing here. You have just two design variables, and we can show the two different approaches here, gradient based and DOE. Because the design of experiments, that's exactly what the Design Explorer in Inspire will do, and it has its use cases, and I like to show why use one over the other on certain or different situations. Okay, basically, you have the code here, but I think it's best to just show it to you. So I have made a little bit of a function here with gradient descent, and there will be a smooth function and a not so smooth function. So that one was the smooth function, which was detailed, and the other one I did not put into the markdown. I should do that. But the other one I will also just simply plot. Basically, it's the same thing, but a bunch of cosinus and sinus laid on top of each other. And so you see, this is more like a hill-valley thing where you have a lot of local minima, right? That's the problem here. Local minima, not so good for gradient descent, right? Okay. All right, so those are the two functions. Now let's dive into the gradient descent. What does it do? Just think about the function, the smooth function again. The smooth function was a smooth, yeah, you can call it smooth. But the function here, if you just think of starting anywhere here on the grid and you're blind and you want to go to the valley. And what you can do is you can take your feet and just measure around your position, where does it go down the steepest. And in this direction you will follow. And that's you're doing until you're not moving anymore. That's basically gradient descent. And if I show that to you, for example, here, so basically we have here the main function, we start at 0, 0, and the smooth function is false, and we just do the gradient descent. I will not go into too much of detail how this works, but you can find that everywhere on the internet. It's pretty common. So if you do that with the smooth function, you can see the gradient descent path. It started here at 0, 0, and then it went down until here, and it found the point 2.99999 minus 0.999, whatever. So basically 3 and minus 1. And the value for the function is 0, or 1 to the power of minus 12. Basically, that's gradient descent. For smooth function, that's perfect. Now, the DOE, let's say DOE is more like marbles on the surface. Like, just imagine you have the surface again, and then just think about you being on top of this surface and doing like a mesh grid with sticky marbles which you drop, and wherever this ball then lands on the surface, it sticks to it. And this is more or less like, or how else could you describe it? Just think about you in a lake, and you can measure with a stick the distance until you reach the floor. But you can do that just a bunch of times, and your problem or your goal is to find where the lake has its bottom, right? At the deepest position where you can be. But you just can measure one point. You don't have any gradient. You don't know how this thing behaves in the neighborhood of your position where you're at. So basically that's DOE, and therefore it's also a lot better for nonlinear problems, right? Because for nonlinear problems, the gradient is not of much value. If you just think about this thing, coming back to the gradient solution, you start at any point here, and then you measure with your feet where does the path go down the steepest, and then you follow that path. Chances are pretty high that you are ending up in a local minima, because whenever you are in a position where every gradient points up, you will not move anymore. And that's what's happening here. But the chance of you dropping a marble into the deepest valley when you're dropping a lot of marbles, this is basically the DOE and the DOE advantage here. But yeah, I have to say, it's in the easiest form, it's really just dropping sticky marbles. They will land and they will not move. There's not something like a combination where you drop a marble and then it sticks somewhere, and then it does a gradient based approach until it finds a local or global minima. But those optimization techniques also exist, just to be clear here. But this here, what I will show here in the DOE, is just you have like X and Y values, which is just a lint space. But just let's do that for, what do we have here? Smooth function should be true. Let's do that for the smooth function first. And this time, this did not go so well like with the gradient-based approach. You see here, it ended up on 2.7 and minus 1.03, and we have 0.05. Close, but not really close. You see also the point here, and you see all those gray dots. Those are those sticky marbles you dropped, and basically you just have what you have, right? You don't do any refinement or so. Okay, maybe I will do just a column map also, that you can... If I just plot this one, it will just give a top-down view. And you see, wherever you have a gray dot, this is a position where you measured how deep the surface is, or what's your evaluation on the function, and it picked just the best one, right? And every gray dot is a function call. So it's pretty expensive compared to the gradient approach, because if you have the gradient approach, you see all the red dots are functions or function calls. So it is a lot less expensive because it reaches the optimum far more quickly in comparison to the DOE. But on a DOE, you can really choose what you want to do, right? So we had here the mesh grid with 30 points here and 30 points there. You could do also just 10, for example, right? So it would be just a 100 function calls, still much, but yeah, but your accuracy will also decrease. Okay, so basically what I want to tell you with this is you have those two approaches. DOE is highly applicable for problems where you have something like a nonlinear surface or nonlinear problem, and you don't really know too much about it. And that's where Design Explorer comes in. And gradient based is when you have something like gradients, like where you know something like a relationship between, for example, the stiffness and the element density. For a stiffness matrix, you can derive the gradients, and so that's a pretty easy shot to do the gradient-based optimization approach there. DOE, more nonlinear. All right, with that being out of the way, I would say now it's time to go into Inspire directly and look at that from a tutorials models perspective. So basically I did that once here, but I will do it just once more again together with you and show you some of the findings. Basically, this is the tutorial which comes with it. So if you go here to help and then on tutorials, you will find this page here. And yeah, wait a second. All right, so file, help, and then on tutorials. So basically what comes up is this. And then you have something like structural optimization tutorials, but also Design Explorer tutorials. So I just thought it would be under structural optimization, but it's really here its own topic. So Design Explorer tutorials. And this is the one we'll be going through, okay? So sit back, enjoy. Now this is the tutorial about with the model. I will just clean the model space again and press F7 to get this demo browser, and then you see under structures you have the Design Explorer DOE fixture model. I just dragged that in, and now we have it here. Basically, something you should always make sure is that the solver is the correct one. So solver being one of two. So you could do the SimSolid solving thing, or you could do the OptiStruct. For simple geometry or something like this, or faster optimization, I would always, or faster, not optimization, but faster function calls, I would always use the SimSolid solver. But it can happen that, for example, if you have something like a connector, which is not supported in SimSolid, it will change the solver. And if you don't be careful about this, it might be the wrong solver. So go to File and Preferences, and then you have Run Options, but not here, but here in Inspire, yeah, Run Options at the Inspire node, and then you have the SimSolid. You can get a bunch of other other preferences here as well. For example, the gravity direction is also available here, and the number of CPU cores. Yeah. All right. Good. So that's being set to SimSolid, which is correct. Then another thing to check also is the unit system. Oh, I'm in the way, right? So the unit system down here can be set to whatever. Let me just quickly go here up so you can see that here. And typically I'm going with the MPa, but the tutorial says that you should use kilogram, Newton and seconds. So this is just a hint on how the solver should interpret the things here. And it's good to set those, that you know what you're doing here. Now that it is a consistent unit system and that you're aware of it. So basically that's that. So that's being set. Now there is the variables. On the geometry ribbon, there's the variables section. Oh, I did not do that in the last step. Wait a second, where is that? Here, variables. You see that there is variables being set here, and we will be talking about what those are in a bit. But basically, during the sketching phase, you can define variables you can then use in the design of experiment or in the design explorer. So basically, you see the design explorer here. This is where we want to go. But in order to be able to use something like the design explorer, we have to create something to work with, like with the thing here. We had to create, for example, here like a linspace for x and y values. We have to create something which the designer or design of experiment scheduler can take and change, right? So this is basically all the things that can be changed for the design of experiments. Okay, so this is the variables. And for example, the tutorial asks you to check if the main tube length is really 5120, because now you can check where this comes from. And one thing to do this is pressing F6, and then you have your design history. And for example, you can double click on here, and then you can see, for example, what are the properties here. For example, here with the fx, you can see that there's something which is assigned a variable to. Or for example, on the extrude, a second, I have to go out here, on the extrude, you can see, and this is a bit hidden, I think, but you can see here that's main tube, and then the value is here, right? So whenever you have a design variable, you can assign it here, and while doing that, this will be then added to this variables list, right? And so this is then being available. Okay, so F6 for the history, then you can go through your things, what you did to create the geometry on this part, and then also add the variables later on a later stage, right? Okay, now let's go to the real meat of this and create the design of experiments itself. Let's close the history, close also the tutorial here, and go to the Design Explorer and on Explorations. Now basically here, this is all the things you have available. If there's nothing here, you have not defined your variables, so nothing to play with, you cannot do anything. But here, you will see then the design of experiments, like the runs you can define. And just by plus and adding a DOE, for example, you can choose which of those variables you would want to include in your optimization, or in your DOE, I should say, because there's a separate optimization also there. But let's be clear with the terms. We are talking today about the DOE, the design of experiments, with the Design Explorer. Okay, so I checked all those variables. So those are all available to me. So I added the space where the Design Explorer can operate on. But now what I also have to choose is how. For example, the design variables by default will be just the value you assigned it to, and then a max value, which is 20% more or less above the value set, and a value 20% lower than the value you set. So this is maybe not the thing you want. For example, the tutorial shows us here that you could change the thickness here from a continuous variable, because maybe those profiles are not available in, I don't know, 8.461 millimeters. So you can choose to change that to a discrete variable. And by doing that, it's that's just the one step of two. You have to then click here and see how it's being done. For example, you can do step size of 0.5, hit apply, and you will see that now the variables are now from 8 to 12, but in 0.5 millimeter steps. So basically that's something you might get when you want to buy those parts. So you can change that and do that for here. Also, sometimes I think, not in this model, but in other models, it could be something like an impossible constraint. So if one variable is at a max limit and the other one is at a min limit, and you have something like a negative volume or so you have to be careful about this. It's not happening in this model because it's pretty simple, but just be aware of that this could happen. Okay, so we have now created the design variables and also how the solver can operate in choosing the different design variables, so the values for it. But now we don't have something what is the response value. More or less, the response value is the same thing as the objective here. So for example, I had this objective, the function. So this is when you put in an x and a y value, what comes out here, that's the objective. That's more or less the response function, the response surface, you could also say, right? So basically that's the thing here you can do. And for the response, you can just add something, and you see there's a lot of different kind of responses you could do. Something like a stress, mass, volume, frequency, buckling from structures perspective, but also motion, fluids. So that's pretty much you could do. And this goes far more into the depth of the possibilities of the Design Explorer, which we might cover in a future video. But for today, I will keep it simple and short, and this will be just structure displacement on the model. And that's it, right? So it's the global displacement. I would say the maximum displacement of the maximum displacement of the magnitude, right? You could also define just the x and just the negative or whatever. But here the magnitude of the maximum of the magnitude is being here as displacement 1. So this is the response value. This is the thing you want to look for, right? Okay, that's that. And let me just simply look if I forget something. I did forget something. Yeah, something you can do is if you want to see what kind of changes will be happening in your model if you change something here, there's a little bit of a slider here which you can use. For example, here main tube L, I know that this is the length of the tube here, and if I just put that up, you see that it will extend. And so you can check if the boundary conditions are in place, if that's what you wanted to do, and also if both minimum and maximum values are feasible. Because as I said, if it's not feasible, you have to check that you adapt your minimum or maximum values or the design variables itself. Okay, so that's that. I would say we are pretty now ready to run. Okay, so we can hit the play button here, and now here's an important thing. So the DOE type, you can see that's full factorial you could choose. Full factorial would mean that you have every combination on your design variables with every other combination. So just imagine if we have something like this here again, and in the DOE we choose to have like x values and y values. And every other combination of x and y values would be a point, a gray marble in the design explorer, or in the design of experiments. And that would be full factorial, but that might be more than you can afford, right? Because if you just think about this it's a small model, but these are 2,300 function cores. That means simulations. So that's a little bit too much. And there's a way of shrinking down that, and the MELS, let me just simply look up what this stands for. Modified Extensible Lattice Sequence. So the lattice sequence is a quasi-random sequence or low discrepancy sequence designed to equally spread out points in a space by minimizing clumps and empty spaces. Okay, so let me choose something for here, and I will talk a little bit more about it during the execution. Let's hit run, and this will now run the 20 runs I just defined. So basically, the problem with randomization is you cannot be completely random. If you're completely random, what might be ending up happening is that you have a bunch of points in relatively similar distance, or distance is also something you have to grasp. But just think if you're here at a simple example again. Here you have x values and y values. Full factorial would be every x with every y combined. So this is the grid, right? This would be like a checkerboard, like a grid. All right, if you do random, like let's just say we do random x and random y, we put 10 points in x, 10 points in y. And if we don't define the distribution, we might getting clusters and not having our checkerboards equally spaced, like, or covered in equal distances. And that's a problem because you might really miss the minimum. Let's just say you're really unfortunate, and all what you're doing is let me just simply go on the smooth function again, that we can see that. Let's just say all your points are clustered here, and maybe some here and some here and some here, but nothing is here. So you will not ever getting the minimum, not even close to the minimum. And that's why you have to spread the variables or the design values evenly across the design space, that you have at least a chance to getting something which is in the neighborhood of the global minimum, right? So it's all about coverage of the design space, like the different design values. That's why you do something like this. Okay, so this is now being run in the background, and I choose to have 4 runs in parallel. So this will just do 4 runs in parallel. You have to check, maybe sometimes it could also be a bit of a licensing issue, or if the model is too big, then you have to check that you have a decent amount of memory and computing power, that it works for 2 or more runs in parallel. If that's not possible, then you just have the option to just have one or 2 runs, like to decrease the number of runs which you do in parallel. Okay, I hope this is not going to completely overwhelm my computer here, because I see I'm getting a little bit of a frame drop here. Okay, but it's almost done. All right, I think this is done now, and we can click on the view results. This will open something like this here. And here you can see the 20 runs. For each run, so for each row, you can see a very discrete set of values for each of the design variables, right? So that means you have an exact value of, for example, main tube T of 8.5 here, main tube B of 115.2 millimeters, and so on and so on. So this is one point in your design space. Just always make sure the comparison to this simple problem, here you just have 2 design variables, x and y. Here you have many. For x and y, it's easy to do something like this, to display the complete response surface on a 3D grid. Because that's something which we as humans can really good, we can understand more or less. But for this thing here, this is a hyperspace of 3, 6, 9 of 10 variables, and then you have a 11th variable which is dependent on those 10 variables. So it's a lot. It's harder to imagine, but from principle thinking, it's just the same thing. You have 10 variables. You could set however you want in the boundaries. This is one run where all the variables have been set to a value, and then the displacement is one of the responses. Oh, sorry, it's 9 independent variables, and displacement is already here. Okay, so 9, but yeah, it doesn't change too much of the thing here. Okay, basically this is the data, and it's maybe not too easy to visualize something which is of value out of this one, but you have more options here. For example, linear effects is pretty cool. Linear effects shows you the influence of certain of your design variables on the response. Could be also more responses, right? But here's just one response to displacement, and you see if you do the FA tube B, if you choose to increase this parameter, it shows that the displacement decreases a lot. So that means this is having a big influence on your response. So if you want to optimize your design for minimum displacement, this should be a thing you're looking at. The other ones, which are also contributing here, is the main tube B and the L1 variable. And so, but you also have variables which, if you increase those, it has a negative or a enlarging effect on the displacement. So you can really see what does a particular variable do to your response. That's pretty cool. So linear effects. Trade-offs, that's also a good thing to do. I find it, yeah, it's useful. This lets you just choose to change a design variable, and then you can look here on the displacement, what's the effect on it. So for example, if this FA2B was pretty significant for decreasing displacement, so if I increase this, you see it's decreasing the displacement value here. So basically you can play around with and see what does this do to your responses, right? But here, for example, doesn't change too much. And then scatterplot is also pretty cool. This is because I have a little bit more of a background in this kind of machine learning things. This is a thing I really like to play around with because it lets you display the relationships between two variables. For example, we had that FA2B, right? I think it takes a bit of time. And then, for example, you would want to have, for example, the y value to be the displacement value. If you have displacement on the y-axis and on the x-axis you have this FA2B value, you see all the runs as dots there. And all those runs, if they are having something like you can really do a linear regression on, you can see the data and see why the linear effects are as they are, right? So this is a thing to check. And also if something has no correlation, you can also see those in those scatter plots, right? So this is a thing to check. So sorry, it's not really, okay, sorry. It's not a double click, it's a click on the radio button here. So for example, FA2B and displacement 1, what would you think, what would happen here? You think this has a positive, negative, or no correlation? If you look back to the linear effects, this is more or less the correlation. This is a negative correlation. But how? Is it linear? Is it more than linear? This is something you can see here. And if I check those, let me do that and this. So basically you can estimate it from here. You see this, that this has a negative correlation, and you can really see how those correlate with each other. Another thing, if you just put another variable, for example, ground plate W, so you can see that this lattice thing at work. It evenly spreaded more or less the design points. It's not like you have a cluster here and nothing here, for example. That's a thing. But other than that, you can see that there's no correlation between those. And there should not be one, because those are not really constrained in any way. Yeah, so that's that. All right, did I miss anything? So scatterplot, cool thing to do, trade-off to play around, that's also great. And the linear effects, definitely to check what is driving your responses. So basically that's it. That's a quick introduction into the Design Explorer. I hope you will use this once for your models. And if you have any questions about it, just leave a comment here or write me a mail. I'm happy to help with those kind of things. And if you have some suggestions about the code or want to get deeper into this one, also happy to hear that. I will put the link down in the description where you find the code on GitHub, so you can also play around with that. And yeah, hope to hear from you soon, and thanks guys. See you later.